All right, open up your book to section 7-4, and we are on page 357 in your book. Title of this section is arcsine, arctangent, arccosine, and trig equations. And the objective is find algebraically or numerically the solutions to equations involving circular and trig functions, that is your sine, cosine, and tangent, functions of one argument. And you'll recall in the first half of this section we talked about the arccosine, or really we refreshed our memory about the arccosine because we've covered that previously. And we dove a little bit further into arcsine, so that leaves us here arctangent to talk about in this discussion. All right, so let's start out with a similar example to what we saw when we talked about arccosine and then arcsine. And now let's talk about that for arctangent. So let's suppose that I've got an equation here that I'm trying to solve, and I want to find all the solutions. So I've got the tangent of x is equal to 0.6, and I want to find all the solutions. So let's sketch a horizontal line that represents 0.6, so maybe that'll be about right here, we'll say. And you can see that you're getting all these solutions right here, which are the solutions that we're going to be looking for. Again, I don't want to find just one of those. I want to find all of those. Now, the nice thing about tangent's a function that's split by these vertical asymptotes. They're not in our sketch, but I'll go ahead and mark them here for us. And you'll notice here that these vertical asymptotes that we're marking there are actually separating our solutions, that there's one solution in between each of these vertical asymptotes. Well, that turns out to be pretty nice here to help us kind of divide up these answers. Well, let's take the equation that they gave us. Tangent of x is equal to 0.6, and look at how we'd solve that. Tangent of x is equal to 0.6. So again, what we first learned when we learned our inverse trig functions is that we would rewrite this as saying x is equal to the tangent inverse of 0.6. So I definitely want to start with that. But again, I know that's only going to give me one solution. And the question then becomes, well, which solution does it give us? And to do that, you got to go back to the definition here of our inverse trig function, and in particular, the restriction that we put on the original function tangent so that the inverse function was a function. So the restriction that we made, we said that we are going to restrict our domain of the tangent function from negative pi over 2 to positive pi over 2, which meant that the range of tangent inverse was going to then be between negative pi over 2 and positive pi over 2. Or that's quadrants 1 and 4 if you're sketching an angle in standard position. That's our range of our inverse trig function. That range is the same as the restriction on the domain of our tangent function. So where exactly does that occur at? Well, actually, I marked a couple of these already. Negative pi over 2 is right here, and positive pi over 2 is right here. Those are the locations of the vertical asymptotes. Now, again, when we first defined these, we defined these in degrees, so that was negative 90 degrees and positive 90 degrees. We're just converting that over to radians here. Negative pi over 2 to positive pi over 2. So the solution that we're finding, we're guaranteed is somewhere between here and here. When I find tangent inverse. And again, which solution is that? Well, again, there's only one there, so it's pretty obvious which one it is that we're finding. It's this one. Tangent inverse is going to give us that one solution there. Now, the problem is I don't want just one solution, I want all of them. So how do I find the rest of these? Well, when we're dealing with arcsine and arccosine, we said the thing to do is add on multiples of the period. And for those two functions, the period of those functions is 2 pi. For tangent, though, the period is not 2 pi. The period is half that. The period is only pi units, or 180 degrees. So if I take this answer and add on multiples of my period, plus pi n, that should give me all the solutions. That is, wherever this first solution is at that I've circled, pi units later is this next solution, and pi units after that is the next one, and so forth. They are differing by pi units once I find where the first one's at. And furthermore, if I want to find out where exactly are these solutions and what values of n do I pick, well, we can do something similar to what we've done when we worked with arc sine and arc cosine. Think of the, I'm going to call it the horizontal translation here. We don't really have a phase displacement when we talk about tangent. We do a sine and cosine for sinusoids, but we don't use that term for those. So the phase displacement for sine and cosine is also known as a horizontal translation. So I'll call it that there. The horizontal translation here is 0. I'm not subtracting anything from x. So at x equals 0, that's where n would be equal to 0. N is equal to 0 right here on my sketch at x equals 0. And it turns out that I go to the right to find this solution right here. So with n equals 0, right there's my solution. Here's where n would be equal to 1. And again, I go to the right and I find that one solution there. With n equal to 2, I find that solution there, and so forth. All right, again, you should be able to look at an accurate sketch of this and know what value of n to pick to find the particular solution that you want, or the set of solutions that you want. If I only wanted the first 3 positive solutions, those are the 3 that I've got marked here, and I'd know to pick n equals 0, 1, and 2 to get those. That actually leads us to our definition of arc tangent. Here's our definition of arc tangent. This is, again, the inverse tangent relationship. This is not a function. This is going to give me more than one answer when I plug in a given value for a. Unlike the inverse trig function, where I only got one output that was somewhere between negative pi over 2 and positive pi over 2. So here we go. If we've got tangent of x is equal to a, then we can say that x is equal to the arc tangent of a. Again, that's going to be the method that we're going to use from this point forward to solve equations that involve tangent. We will not use tangent inverse anymore immediately to solve those problems. We'll write it in terms of arc tangent. We'll keep that in our problem until we finally get the variable over on the left isolated by itself. In this case, it already is, but there could be other stuff over there. Once I've got it isolated by itself there on the left, that variable, then I can go and replace arc tangent with what it's equal to. Arc tangent, what we just found, is equal to the tangent inverse of a plus 2 pi n. Tangent inverse of a plus 2 pi n, where n is some integer. Now this is in terms of radians. If you wanted to switch this over to degrees, you can definitely switch it over to degrees. Just use your conversion to do that. Pi radians is equal to 180 degrees, so you'd be adding 180 degrees times n instead of adding pi radians times n. But you can do a conversion there, of course, for any one of these 3 inverse trig relationships. Just make sure you replace all of the pi's that you see in there with the appropriate conversion. All right, we talked a little bit further about the arc sine relationship. We should do the same discussion here about arc tangent, that when you're solving equations algebraically with arc tangent, it's critical that you understand the domain and range of that inverse trig function and how it helps you find the solutions that you're looking for. So the range of your inverse tangent function, we already defined, was from negative pi over 2 to positive pi over 2. Notice that we're not including the endpoints here, because tangent is not defined at those endpoints. It's undefined there. That's where the vertical asymptotes are. That corresponds to quadrants 1 and 4, just like we saw with sine, or sine inverse. The range is all real numbers, from negative infinity to positive infinity. And again, the reason for that is we've taken the original tangent function and we've restricted its domain from negative pi over 2 to positive pi over 2. That's 2 vertical asymptotes. And the function stretches all the way from negative infinity to positive infinity in that particular domain. So if you take that domain and range and swap them around, you now have the domain and range for the inverse tangent function. All right, so the question then becomes, just like we saw with arc sine, well, what happens if we're dealing with an angle that's in the first quadrant versus the fourth quadrant? The good news for us here is that we really just kind of tackled the first one of those two questions. And the fact that the example we worked with, we were finding the tangent inverse of a positive number. That means you're in the first quadrant. So it will look very similar to what we just had on the board here on the previous slide. But let's go ahead and sketch this. If we have the tangent of x is equal to a, where a is positive, what happens? So a is going to be some positive number. I'll pick it to be some value up here. This will be a. So how do I find a particular solution here, and where are my solutions? What direction do I go? Now again, the nice thing about tangent is tangent has these vertical asymptotes. This pretty much divides this up for your values of n for you. The nice thing about tangent, and I think there's no mystery in determining what value of n do I pick to find a solution, and do I go to the left or right? Because of these vertical asymptotes, it makes it a lot easier for us. But let's go through and make sure we understand how to do that. Again, look at your, it's not phase displacement here for tangent, we call it the horizontal translation, but look at that d value there that you're subtracting from x, which in this case is 0. So that tells you your starting point. So here's where n is going to be equal to 0. So to find that first solution, I'm going to head to the right. This is going to be n equals 0, and that's the only solution that I get there. That's my tangent inverse solution. That's the one and only solution that I'll see there. And then when I let n be 1, this is where n is equal to 1. Again, that's where we're crossing the x-axis there. And if I move to the right, I'm going to find the one and only solution there on that particular part of the domain between those vertical asymptotes. Is right there. Here's where n is equal to 2. And here's where n is equal to 3. And of course, you can go in the negative direction as well. So if I go back over here to the left, I can say that this is n equals negative 1. And there's that solution. If you want to find the first negative solution, I'd pick n equals negative 1 to find that first negative solution here. Okay, this is what it looks like if a is a positive value. What happens then if a is a negative value? Remember, with arc sine, we found out you end up with something that looks a little bit different. So that's why we investigated that a little further. Let's do the same thing here with arc tangent. Let's take a little closer look at it. So if we have a being a negative value, with a being a negative value, that means that a is below the x-axis, so we'll pick it to be somewhere down here. We'll say that this is our value of a. It's a negative number. It's below the x-axis. And again, to find the solutions then, these vertical asymptotes, I'll go ahead and mark these in here again, but those really nicely split up your solutions that you're looking for. So to find that first solution, again, think about your horizontal translation here. It's not phase displacement, but horizontal translation here for a tangent function. That's x equals 0. So that's our starting point. That's where n is going to be equal to 0. That's how we're always determining where do we start. Look at that horizontal translation. That's n equals 0. And again, what we saw up above was that you move to the right to find that solution. Well, if you move to the right here, there's no solutions over here on the right side. You have to move to the left to find that solution. So you do have to move different directions to the left or right, similar to what we saw with sine when we do this. But I think this is a lot easier because there's only one solution between these vertical asymptotes. You don't even have to worry about, do I have to move left or right? Just look for the only solution that's there and move in that direction. Not quite as easy with sine. With tangent, I think this is pretty straightforward. There's only one solution there. Move towards it. Move to the left. So this solution that you see right there, that's the tangent inverse solution with n equals 0. If you wanted to write down for this time the first three positive answers, you're not including n equals 0. Here's where n is equal to negative 1. You're not including that one either. That's even more negative than the previous one. The first positive solution, the first one that's to the right of the y-axis, here's where n is equal to 1. This solution right here, as I look at all these solutions that I'm circling here, that's the first one that's to the right of the y-axis. That's the first positive one. Here's where n is equal to 2. Again, in this case we're moving to the left, but I'm really just saying find the only one that's there, which means I have to move to the left to find it. Here's where n is equal to 3, and there's our only solution there. So yes, you do have to move in different directions like we saw with arc sine, but the direction is pretty much given to you because there's only one solution to find. Find the one and only solution that's on this section of the curve. Move left or right, whichever way it has to go. Doesn't matter. All right, so let's take a look at an example. This is example number 2. We're on page 359 in your book, and it says, solve the equation 4 tangent of 2 theta equals a negative 5. 4 tangent of 2 theta equals a negative 5. And they want us to find algebraically the first 3 positive values of theta. So they didn't give us a domain here to work with, but they just simply said find the first 3 positive solutions. That is what we're looking for. All right. Now, if you wanted to, you could start out with a sketch of this and use that to help you see what values of n you're going to pick to find those solutions. In fact, let's go ahead and do that. We can actually sketch what this thing looks like. We're looking for the first 3 positive solutions, so I guess I really want to start to the right or move to the right of the y-axis here. I've got a vertical dilation factor of 4. I've got a horizontal dilation factor of actually a half. And I've got a value of negative 5 that I'm setting this equal to. So the dilation factors just stretch this in those 2 directions there. They don't really change what the graph looks like. So I'm just going to sketch it like this. And then we'll mark some key values here on our sketch. So the period of this graph, again, because of the fact that it's a tangent of 2 theta, to find out what the period is, you can take 108, this is in terms of theta, so this is in terms of degrees. You can take the 180 degrees and divide it by the period, and that gives you b, or in other words, the period is 180 over b. In fact, let's write that down. Period is equal to 180 degrees. If this was in radians, then we'd have pi instead of 180 degrees divided by the absolute value of b, and its absolute value because b could, of course, be negative, but period is always positive. In this case, b is equal to 2, so this is equal to 180 over 2, or that's going to be, maybe I'll write it that way, 180 degrees over the absolute value of 2, or that's 90 degrees. You need to figure out what the period of your function is, and then you can sketch in these key values. So since the period is 90 degrees, that means these first vertical asymptotes that I see here must go from negative 45 to positive 45, so that the distance between them is 45 degrees, or is 90 degrees, and that 0 is right in the middle of those. And then we can add 90 onto that. This is at 135. Add 90 onto that. We got 225, and then 315, and so forth. All right, so we know where these vertical asymptotes are. All right, we're trying to set this equal to a value of negative 5. So let's mark our negative 5. We'll put it down here somewhere. Now, I've actually got 4 solutions sketched here, but again, they only asked us for the first 3 positive solutions. So I want this one right here, and I want this one right here, and this one right here. This is a big no right here. I'm not interested in that one because that one's negative. It's to the left of the y-axis. But notice what values of n we're going to have to use here. Again, our phase displacement here, if I look at what value I'm subtracting from the theta there, it's 0. So at theta equals 0, that's where n is equal to 0. So this is n equals 0. And notice that with n equals 0, you'd be finding that solution right there, which we said we don't want. Here's where n is equal to 1. I want that solution, so I'm going to use n equals 1. Here's where n is equal to 2. I want that solution. Here's where n is equal to 3, and I want that solution. Before I even started this problem, before I even came up with the algebraic solution, I know what values of n I'm going to pick at the end. N is going to be 1, 2, and 3. Again, you don't have to start out by doing this, but I want to point out to you that I know that answer, that part of the answer, before I even start the problem. All right, now let's do the algebraic solution. So we've got 4 tangent of 2 theta is equal to, what was that, a negative 5. All right, we're going to go through and solve this the same way we've seen how we solve these, whether it's in terms of sine or in cosine, or in this case, tangent. Go through the same steps. First step is to divide by the 4, so I'll end up with the tangent of 2 theta is equal to a negative 5 over 4. Or if you want to rewrite that, negative 5 over 4 is what, a negative 1.25. You can write it that way if you want to. As long as it's a nice number, I'd say that's okay to do. If it turns out to be some decimal that doesn't terminate like this, I would suggest you leave it in the fraction form. And now solve for theta, actually 2 theta. 2 theta is equal to the arc tangent. That's the new step for us there. We are not going to write down tangent inverse because at this point, because I'm only going to get one solution with that. Keep it in terms of arc tangent of a negative 1.25. Solve for theta over here. Isolate the variable on the left side, so divide by 2. So theta is equal to 1/2 arc tangent of a negative 1.25. And now that you got the variable isolated on the left side, now you can actually replace arc tangent with what it's equal to. So we have theta is equal to 1/2 times. Now remember, we're doing this in degrees here for this problem. So when you go to add on your multiples of the period at the end, make sure you use degrees there. So we have, I'm going to go ahead and put this in parentheses so I distribute this 1/2 all the way through here. But I've got a tangent inverse of a negative 1.25 plus, and then instead of pi n, because that's radians, I'm doing 180 degrees times n. And now let's distribute that 1/2 through there. We should distribute that at each time here. So I got a 1/2 tangent inverse of a negative 1.25, or a negative 5/4 if you left it like that. And then half of the 180 is going to be 90 degrees. Remember the significance of that value at the end there, 90 degrees times n. It's always the period times n. If you go back up to our sketch, or even what we wrote over to the right there, we already said the period is 90 degrees. We know we better end up with plus 90 times n at the end, and that's what we got. And actually, we've already done the work here to find our values of n. We said n has to be equal to 1, 2, and 3. There's our answer. And you'll leave your answer in that form just like that. Write an answer that's in terms of n, and then figure out what values of n you've got to plug in to get the solutions that you're looking for. All right, and that is the end of the second part here of section 7-4.